Hi, Chris Good here, and this is part 2 of our video on the analysis of variance. And we're going to use the data that I used in part 1 to, as an example, to calculate the test statistic for ANOVA, which is F. And there's a couple of new notation things that you need to know. The first is that K. K is the number of treatment conditions that you have. In this case, we have K equal to 3 because we have the Mozart, the relaxation tape, and the silence treatments, so K is 3. Little n now is going to represent the number of scores within each treatment. So you can talk about a little n for Mozart, or the first treatment group, little n for relaxation, and a little n for silence. And in this case, we have the same number of scores in each treatment, same number of participants in each one, but that's not always true, and you can do ANOVAs where you have unequal groups, as long as they're fairly close to each other in numbers. Big N, then, is going to represent the total number of scores in the whole study. We have 5 in each group of 3 groups, so the big N has a total of 15. And T is the total, or the sum, of all the scores within a single treatment condition. So you'll see in a couple of slides we have a T for the Mozart condition, a T for the relaxation condition, and a third T for the silence condition. And finally, as I mentioned in the previous video, G is the grand total, or the sum of the scores for the whole study. That's all 15 scores added together. It's not the number of scores, it's the sum of all the scores for the whole study. All right. With these new variables, we can calculate everything that we need to do our statistic. And there's a third video that I've posted, and that's me sort of going step by step and doing all the hypothesis testing steps to calculate F and to make our statistical decision. And so please go ahead and watch this. Right here in this video, I'm just going to walk you through all of the equations. All right. So you don't necessarily have to calculate the total, but you should know how to do it. You don't need to do it to answer the question, but I may ask you to do it on an exam or a homework or something like that. In fact, there's definitely a homework question about the total sums of squares. But you already know how to do that. You just need to treat all 15 scores the same and sum the square of each one of your 15 scores. We have 15 in this case. Subtract the sum of all of the scores squared divided by n. Those two things are different. The square of the sum is different than the sum of the squared scores. But we have a new name for the sum of all the scores. It's G. So the total sums of squares, this is the sum of x squared, sum of each of the 15 scores squared, minus G squared over big N, right? It's the total number of scores that you have. So we're substituting big N in this case in our computational formula. Notice also that G, the grand total, is equal to the sum of the individual group totals. It's the sum of T for Mozart plus T for relaxation plus T for silence. Okay. So, one thing that you should definitely keep in mind, and this may end up saving you some time on a future quiz, hint, hint, is that the total sums of squares, and you might be given this at some point, is equal to the sum of squares between treatments plus the sum of squares within treatments. In fact, this is what analysis of variance is. It is dividing the total variability into the variability between your treatment groups and the variability within your treatment groups. So keep this in mind. Sum of squares between treatments and sum of squares within treatments sum to the total sums of squares. All right. The within treatments sum of squares is simply equal to the sum of each condition's sum of squares, and I've calculated those in this data set right here. So what I've done is I've subtracted the mean from each one of the scores in the Mozart condition. So the mean's 4.8, 5 minus 4.8, 7 minus 4.8, 4 minus 4.8, 4 minus 4.8, do it a third time, and then for each one of those we squared those deviations and then summed them all up. You guys have been doing this since 3510, so Very easy to get sum of squares for the Mozart condition. Do the same thing for relaxation. Happen to have the same number for the silence condition. So to get the total sum of squares within treatment groups, you simply add those three numbers together. Add the sum of squares for each treatment condition. If you knew the sum of squares for all 15 of the scores, which you could get by subtracting the overall mean from each one, or you can use this computational formula that I just showed you, the sum of the squared scores minus g squared over n. All right? You could subtract SS within from the total, and you'd have SS between. And again, keep this in mind, because in a future quiz it might help you out. But you might not know the total sums of squares, so there's a computational formula for the sum of squares between treatments as well. And it's the following. So the sum of squares between treatments is equal to the sum of the t squares divided by n for each treatment group. What are the t squares? Remember, t stands for total, and t, you have three t's here. T, there's a t total for the Mozart condition. That's just 5, 7, 4, 4, and 4. Right? 12 and 12 is 24. So that's the total within the Mozart condition. We have a total within the relaxation condition and a total within the silence condition. And we're going to square those t's and divide by the number of scores within each condition. So t squared, 24 squared, divided by n, which is 5, plus 18 squared, that's the t squared for relaxation, divided by little n, which is 5, and 13 squared, right, that's the total for silence groups, squared, divided by little n for the silence condition, which is 5. Now, n was the same in each one of these groups, but like I said, it isn't always. And then we subtract from that sum g squared, the grand total, over big N. So you can come back and check your math if you want to try this on your own and follow along with the video. But it's 24 squared over 5, 18 squared over 5, 13 squared over 5. Add that all up together, right? And you subtract 55, which is the grand total, squared, divided by 15. The number that I ended up getting is 12.13, right, with a little bit of rounding. And that is the sum of the squared deviations between the treatment groups. SS within was pretty easy to get. I just had to add up the SS's that I calculated before. So SS within is just the sum of the sums of squares within each treatment group. My answer for that was 25.2. All right. Why are we doing this? What is the point of all of this? Well, the point is to find what the F ratio is. And F is the ratio of the variance between treatments to the variance within treatments. You guys know that variance is sum of squares over degrees of freedom. And that's exactly what we calculate, but we don't call it variance. We call it the mean squared, which is kind of what that is short for is the mean squared deviation from the mean. Right? We have two types of mean squared deviations. We have between treatments mean squares and within treatments mean squares. And it is variance. I actually don't know why they called it mean squared instead of variance, but that's what it is. It is variance. So we have sum of squares between treatments divided by degrees of freedom between treatments. That's the variance between treatments, but again, we're calling it the mean squared between treatments. How do we get these degrees of freedom between treatments? Well, if you'll remember from the previous video, degrees of freedom between treatments is the number of groups you have, the number of treatment groups minus 1. We add 3, so we have 2 degrees of freedom between treatments. And if we go back to our data here, we would just divide 12.13 by 2. All right. Mean squared within treatments is the sum of squares within treatments, what we just calculated by adding up the sums of squares within each group, divided by degrees of freedom within treatments. And in the first video I showed you degrees of freedom within treatments is the total number of scores you have, we have 15, minus the total number of groups you have. You take 1 away from the total number of scores for each treatment group you have. That was 15 minus 3 is 12 degrees of freedom within treatments. So we would divide this number by 12 to get our variance within treatments, or our mean squared within treatments. Then it would be easy to calculate f, and we would compare that observed value of f with the critical value that we look up, and we'd have to go across to 2 degrees of freedom in the numerator, down to 12 degrees of freedom in the denominator. Numerator, denominator, well, that's just referring to the F ratio. The numerator is the between treatments measurement, so we use our between treatments degrees of freedom. The denominator is on the bottom, and that's the within treatments mean square, so we use the within treatments degrees of freedom. We use both of those in this table right here, and again, the entries in light phase type are critical values for 0.05 level of significance, or alpha equals 0.05, and the bold phase type values are for the 0.01 level of significance. Now, look at the video where I've applied all 4 of the steps to solve this problem and use the hypothesis testing method that we've been doing for the t-test. We're going to use the same thing in ANOVA with writing out the null hypothesis, etc., etc. Check out that video, and if you have any questions about those steps. Now, at the end of that video, we ended up rejecting the null hypothesis, right? That their treatment has no effect, and concluding that it does have an effect. If you do that, you'll need to do some test after the fact to find out where those significant differences between individual groups lies. We call these tests that we do after we find an overall effect of the treatment, right? And let's go back to our data. If we find that these means are significantly different, that there's a difference among these means somewhere, you still won't know which it is. All F tells you is that somewhere among these 3 means there's a significant difference, but it doesn't tell you where it is. You have to do a test after you find that out. We call those tests post hoc tests. I'll describe 2 post hoc tests for you. I'm going to ask you to calculate one of them on the first ANOVA quiz, which is 2 weeks from our next lab session. And in the post hoc tests, we're going to talk about 2 of them. The first is Tukey's honestly significant difference. It's actually very easy to calculate because by the time you get to this point, you have almost everything that you need to calculate the honestly significant difference. This just tells you how far apart 2 means have to be, right, in order for it to be a significant difference. So if your HSD was 2, right, and you have a 2.2 difference between Mozart and silence here, right, 4.8 minus 2.6 is 2.2. And you don't need to worry about the direction. It just needs to be 2 points, right? So if HSD was 2, this difference would be significant between Mozart and silence. But these 2 differences, Mozart versus relaxation, not significant. And relaxation versus silence would be not significant as well. Make sense? I think so. Okay. So to calculate Tukey's, that difference that you need to show for it to be a significant difference is equal to Q times the square root of ms with n over n. We already calculated ms with n here. It's the sum of squares within treatments divided by the degrees of freedom within treatments. And you would divide that value by n and take the square root. What on earth is Q? Well, there's a table in the back of your textbook that shows you how to look up what Q is. Q is the studentized range statistic, and you don't even need to know that to use the table. The table's pretty easy to use. For K number of treatments, you look that up in this row at the top. We had actually 3 treatments, 2 degrees of freedom, 3 treatments, and that's a difference between this table and the F table. Make sure you're looking for K, not degrees of freedom. So K is 3. We had 12 degrees of freedom in the error term. What this means is in the in the denominator of the F ratio. The denominator of the F ratio. What degrees of freedom did you use in the denominator? And I know it says error term. There's a reason for that. We had 12 degrees of freedom in that denominator. 3 different treatments. And again, the light phase type is the value for Q with an alpha of 0.05, and the bold phase type is Q with an alpha of 0.01. So here we would do 3.77, that's our value for Q. 3.77 times the square root of ms with n over n, and we'll do some practice problems to show you how to apply that. The last thing I'll mention is there's another post-hoc test. There's actually a lot of post-hoc tests. We're only talking about 2 of them. Tukey's HSD is one. The second is Chaffee's F-test. It's a little more conservative than the HSD, and it's basically calculating an ANOVA for 2 treatments at a time. So you do the MS between only 2 treatment groups, right, divided by the MS within just those 2 treatment groups. And I won't ask you to calculate that, but you should know that it exists. All right, that's it. I'll see you next time.